Okay, we're back and we're doing C++, object-oriented C++. But we're still covering some... Hello? Hello. Okay, good. Now we're back. We're all back now. And we're going to cover where we left off at the last time. This is still lecture 2, but it's like 100 slides on this lecture, so it's a lot of stuff. So you Java people will like today because we're going to talk about stuff that's not part of Java. That unless you have taken a C++ course before in the past, you probably, or a C course, you probably are not familiar with this concept. And the concept I'm going to talk about today is structures and unions. And then I might even get into classes depending upon how long I talk for. But that is the focus for today. And what we're looking at is this category of structured data types. By definition, a structured data type is more than one, or it's user-defined. So abstract data types fall into this category. Unions, and structures, which are multiple pieces of data all stored together under a certain type. And then we have arrays. And the array example is, more than one. Most of us know about arrays, actually, to some point. We're going to hit arrays just anyway, but we'll hit them after structures and unions. Because a lot of people have some confusion with single and multiple dimension arrays and past multiple dimension arrays and what they're used for and stuff like that. Now, I like to talk about arrays as well because it makes sense when I start talking about pointers and how arrays are passed to functions and they end up being by reference instead of by value. But let's talk about structured data types, which is our main category for today. Our topic of the menu of today. So structured data type is a type in which each value is a collection of component items. So that's another way of saying more than one. It's a collection or grouping. So the entire collection has a single name for the component, and then that can be accessed individually. Same concept as a class. In other languages, however, like Java as an example, we have the class. We don't have structures. We don't have unions. We don't have any, we don't have these capabilities. We don't even have enumerations either. It's often related to information of various different types that are all stored together for convenient access under the same identifier. For example, let's talk about animals. We're going to the zoo. This comes out of the textbook that I have in the syllabus for this course, actually, which is not a bad book if this is your first C course. Hopefully you have gotten the book or have access to it. It's also in electronic form as well. And this looks like a class because most people have done this backwards. You've taken an object-oriented course in another language, perhaps, and you're familiar with the class construct, but you may not have seen a structure. It's actually kind of similar, but it's basic. So there's a lot of similarities between the two, and covering structures actually helps us understand classes a little bit better as well. The C version is the structure. The C++ is the class. We don't have inheritance. We don't have interfaces. We don't have a lot of other stuff with structures that we do with classes. So we have to talk about this animal as an example. And this animal has a .id, a .name, a .genus, a .species, and these would be data members of the function, which is where that members terminology comes from. When I said function, I meant structure. The structure contains members that are associated with pieces of ID. So before structures came along, let's say we wanted to store information about an animal. We could have animal ID is equal to a number. Animal name is going to be a string. Animal, all the different categories. And we have like, what do we have here? We have 1, 2, 3, 4, 5, 6, 7, 8 different variables where we could all store 8 different pieces of data about the same concept. So structures came around as a means to put it all together, encapsulate it under one. And then we use the dot, and this is the first use of the dot notation actually in C++, where we said this animal dot ID, this animal dot name, and then we were able to get at the different pieces. And a lot of people look at this and go, well, why not just use an array? Well, arrays in almost every language all have the same data type. So you have an array of integers, array of floats, array of something, strings. And you can't mix and match data types inside of the array. So here we've mixed and matched data types. We have strings, floats, doubles, anything we want inside of the structure, and we've actually put a name, an identifier to each one of the pieces of data inside of the structure as well. And so here we have thisAnimal, and just like a class, each instance or each variable that we create of this particular data type, and what we're doing is creating a data type. Another animal might have different names, might have different information stored for each one of them. So this is what it actually kind of looks like. And I'm going to combine this example with a few things that we've covered already. I believe I covered enumerations very briefly last time, so let me enumerate more on the enumerations. And we created an enumeration. If you we were here last time and you looked at it, it's nothing more than attaching labels to integer values. So this is 0, 1, 2, and 3. But we don't have to remember that 0 is poor, and 1 is fair, and 2 is good, etc. Instead, we can just assign it poor, fair, good, and excellent. And we're calling this health type as an example. So enumeration health type, this is the declaration that defines our enumeration. We usually see this before we start using it. Otherwise, C++ gives us an error message. Or we see it in a header file or in some sort of included file where we have a bunch of stuff defined. So here's our structure. And this is our formal declaration of the structure. And we declare the structure as a data type. And it does not allocate any memory. We're just declaring the data type. Until we start making data variables of this particular structure, that's when we start allocating memory. Interesting thing, it looks like a class declaration actually, but it looks like just a bunch of data members. We can actually put functions in here. I'm not going to bother. Because once we start putting functions inside of a structure, we're looking like a class. We might as well just save that for the class. The class was, this was before the class was invented. So this came along first, and we went, oh, if we have a structure, let's put all this stuff together. And it was primarily used to bag all this stuff together into one. So we use the keyword structure, and we say animal type. And so we're creating our first abstract data type called animal type. And in here we have a long ID, string name, string genus, string species. Here's our health type. You're like, where did the health type come from? It's that enumeration that we created. So we actually have two data types here. We've created our two abstract data types. We used one with an enumeration and created health type, and then we're creating another one, animal type, and we're putting one inside of the other. Health type health is the name of the variable that's going to keep track of the health type. And health type is going to have a legal value of poor, fair, excellent, good. And then down here in the bottom we can declare variables. And everyone's going, don't those look like instances? I think this was before object orientation came around. We didn't call them instances. We actually called them variables. But believe it or not, in C++, all variables are objects. So we have to work backwards in kind of thinking that, okay, so these are objects, and we're creating instances of objects, but we're still calling them variables at this point. And we use the data type. So how do we initialize a variable? We data type space the name of the variable, and we put a semicolon at the end. So we have animal type, thisAnimal, semicolon, animal type, another animal, semicolon. Just like saying integer I, integer A, integer B. We can put them all on same line. We can assign them values if we want. But if we said this animal is equal to 1, we'd have a problem, because this animal is, well, what is 1? We actually have to refer to this by thisAnimal.id, thisAnimal.name. Hey, TA, can you tell them to stop playing basketball next door? Thank you. Because that's going to be irritating after a while. Yeah, the banging of the basketball against the wall. You'll also notice at the end of the structure there's a semicolon. Different, we don't put semicolons at the end of classes. And this is out there in our main program file. This is out there in main, right after main. In fact, it's not inside of main. Main is a function. So we have structures out here that we define, and then we have main, and we're going to use it, let's say, use it inside. And we'll see some examples coming up of how it's being used. So here's our syntax for the structure type declaration. We have structure, the type name that we're creating, and then the member list. And as I mentioned before, we can actually put functions in here. But I'm not going to show you that. Nobody does that. So you might be wondering, well, why in the world am I even showing you structures? Now that C++ is along, we have the class. The class is the end-all of everything, right? It's like the only abstract data type you need, right? No. Why bother creating a class when you can just create a structure? I mean, if it's going to be a lightweight, it's going to use less memory. You're not going to use it with inheritance. You're just going to organize stuff together. Structures are still being used, actually, even with classes, even with object orientation. And it's one of the power that C++ has. You can work backwards. You don't have to program in a pure object-oriented environment. Sometimes it's easier just to have a structure and use it because you want to keep track of some information. It's like, why do people still use arrays? You know, because it comes in handy. so does a structure, and we'll see in a couple of different examples how the structure is actually used. But this is something we don't have access to in Java, but it comes in handy, actually. And I kind of sometimes wish there was a structure in Java, because then, you know, why does everything have to be a class all the time? So, all right, so in the member list, we have the data type, member name, data type, member list, where we actually make instances. So the structure declaration names a type and then names the members of the structure inside of it. It does not allocate any memory for any variables of that type. It doesn't do anything. All it does is declares that it exists. So essentially you can declare as many structures as you want. It doesn't allocate any memory. Your program doesn't run slower or faster with all of these declarations. It doesn't matter. You still need to declare your structure variables when you're using them. So the structure type declaration. If the structure type declaration precedes all of the functions, it will be visible throughout the rest of the program. So it's kind of like that first assignment where you got to create a function first, and then you can create main and you can use your function inside of main, call it from inside. It's order of precedence in terms of what has been declared first in sequence as you go from the top of the program to the bottom of the source code. Same problem with structures. Just like a function, if you put it up first, the rest of the program finds it. If you place it within a function, only the function can use it. It can be used inside of a function. It can be used, well, it is actually used a lot inside of functions. It can be used outside of a function. It's commonly placed in what's called a header file. So what we have now, it's common place for the structure declaration is with type names in a .h header file, and we have the class, the include that file inside of it. So far we've looked at header files for iostream.h, for string.h. Those are built in. Now we're talking about creating our own header files, and we can have a header file that has all of our structures that we're using. So it allows us to actually build abstract data types, make them part of our language, include the header file. So oftentimes what you'll end up looking at when you start looking at somebody else's code, you look at the top and it'll say, you know, functions or something, or definitions of something or other, .h. And then inside you see all of these, you know, what is that? What is that? What is that? And they're using all of these made-up data types. Because this header file will have the enumerations in it, we'll have the structures in it, we'll have the type defines, we'll have everything. And then you've got to customize the language, essentially. You're extending the functionality of what you're using, and you just use the structure when you need the structure. I mean, especially, and you can use structures inside of classes if you want to. You know, so one of the data members inside of a class can be a structure. No limit to that. So it kind of gives you a lot more flexibility, a lot more extendability over the common, you know, just using a class. So it's possible for members of different structure types to have the same identifiers as well. Also, a non-structure variable may have the same identifier as a structure member. So which means you've encapsulated it inside of the structure, then it's inside of the structure. You can use the same name over again. So this animal, that animal, they all have the same name. As an example, it's a variable name. And then as I mentioned before, this is the first exposure to the dot notation. So the member selection operator. Not the scope resolution operator that we looked at last time, but the member selection operator is the name of this one. So after the structure type declaration, say that you know, animal type space this animal type space another animal. This is what I was mentioning before. We use the dot notation to say we want the weight of this animal, we want the country of another animal, or county, you know, country of the other animal. And so here's some valid operations on structures depending upon its type. So we have this animal.age is equal to 18. Okay, now everyone's looking at it. It looks like instances of classes with the dot notation. It is. It's the same concept. If you're familiar with it in any other language, it's consistent. Cn thisAnimal.weight. Get line cn thisAnimal.species. You can use it any way you want. Any type of function calls, any type you can use as a parameter to a function. This animal is equal to name dot is equal to giant panda. Here's an array of animal types. And we've got this animal dot genius 0 is equal to 2 upper. Change this to an uppercase. So it's now a function call used as an assignment to an array index number. And this animal age plus plus. So any legal operation essentially that you can do on any variable, you can do on any member function of any data member of any structure. That's what I wanted to say. We also have aggregate operations that we can do. So an aggregate operation is an operation on the data structure as a whole, as an aggregate, as opposed to each one of the individual components that are part of the structure. So I/O arithmetic and comparisons of the entire structure variables are not allowed. This is one of the interesting things about C++ is it's inconsistent within the language itself. You can't do I/O on the entire structure, which, okay. So operations that are valid on the entire structure would include assignment to another structure variable of the same type. So think about all the rules that are associated with built-in data types in C++ and apply them to structures. You can't take an integer and a float and add them together. You have to take one structure with another structure. Just because they're all structures doesn't make them equal. This animal and that animal, if you have two different structures declared, one's this and one's that, then you can't say this is equal to that. It's two separate structures, two separate data types, all create nothing is similar in terms of what you're looking at. And then pass to a function as an argument, you can pass it by reference or by value. Use the, we'll talk about that. Actually, we talked about that already in the last class. We talked about using the ampersand symbol to pass a variable as an address of the variable. We can pass the address of the structure and treat the structure as a pointer structure instead of a regular value structure and pass it by reference to a function. It can also be returned as a value of a function. So we can have functions of data types of our structures. Which comes in handy, actually. So here's some examples of the aggregate operations. And what do we have going on here? We have another animal is equal to this animal as an assignment. If they're both of the same structure type, we can assign one to the other. And we can write it out. Write out this animal. It's a value parameter. This animal to write is a function. This is a function call to write out, and we're sending out a parameter, this animal. Change weight and age this animal. We have a reference parameter, let's say, for example, that we're using in this function call with, or returning the value. This animal is equal to get animal data, running a function call. You don't see the functions, so it doesn't. You have to imagine that they exist, these functions, and these are legal function calls. It can just be used in all these different ways. Here's a write out. Let's take a look at write out. Write out is being used here. We're sending this animal, the structure, as a parameter to the write out, because we're going to send in the structure to this function and write out all the values about all the different pieces of information that this structure contains. So here's void write out. We're using void because it doesn't return anything. Write out, and the input is animal type space this animal, which means we're taking an animal type we defined as a structure. So we're taking as a parameter, it only takes one parameter to this function, and we're sending it to this animal. So we can send it as an aggregate. Very common. Because you want to, let's say you just want to print to the screen all the items that are associated with this. This could be a record for a student as an example. It would be name, address, phone number, all the information associated with the student. Send it all as an aggregate all together. So it prints out the values of the members of this particular animal. When the preconditions and the postconditions, this is the syntax that most of my lecture slides actually use. In terms of the precondition, all the members of the animal are assigned. As the post, all members have been written out to the screen, which means before this function call, we've assigned, hopefully, a value to all of these structure members, data members. And then as a postcondition, after the function runs, we're going to print it out to the screen. And what we see now is cout, 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 and we're using the dot notation to print out all of the pieces that are part of this aggregate that we sent of this animal. And then we're going to write the word, this is another function call, animal, thisAnimal.health as an example, to print out that enumeration value. Passing a structure type by reference. So the dot notation is actually, and this is kind of my introduction to how arrays are actually implemented. In the C++ language, we always have a starting address. And the starting address is the piece of memory that we're reserving for the particular variable. And believe it or not, even classes work this way. And because we're all statically allocated, nothing is dynamic. So compiler goes through and says, oh, we want a structure, or we want an array, or we want a class. We say, well, how big is this thing? Well, it looks at the structure declaration and says, well, we got 5 data members and 2 functions. Oh, okay, good. And you allocate, the compiler goes out and allocates at some starting address. We have 2 integers. So we got 1 integer, 2 integer, and then we got a float. Okay, a bigger float. We have all these functions. And it says, oh, okay, we need 30 spaces, 30 bytes or something, kind of figures out what it's supposed to need given its settings, its parameters. And then it returns back, and the variable stores the starting address of all this. And then we can actually use it as a reference, and we have the dot in a structure. As we mentioned before, we have the dots that give us all of our points for each one of our data members. So we have dot name, dot address, dot phone number. But it's actually stored sequentially in memory. So when we use the dot, we're actually going starting memory address 9544, go 2 spaces, go 3 spaces, and the name of the structure elements is giving us our how many spaces we need to go through. And it's really named memory space if you think about it, incremented. So when we say dot name, the compiler knows how to go out and find it from the starting memory address, wherever name is. Well, it's the second data member, so it's number 2 space, number 3 space. Same thing actually works with arrays and how they're implemented in C++. Exact, almost identical. But instead of saying name, ID, address, phone number, stuff like that, in the array we say, give us 10. And it's all integer values, so all the spaces are the same size, as an example. And our index value is where we go, give me element number 1. It goes 0, 1, here it is. And we address it by numbers, index values, instead of names. So if you think about the concept, the implementation in the language is practically identical. A structure is sort of the same as an array implementation-wise, except for we have named locations instead of index values, and we have various different lengths of memory that's reserved for it because we can mix and match data types. So classes are implemented in the same way, actually, by the language. So why do you need to know about the implementation? It helps you understand the language from a, from a programming language concepts kind of perspective, I guess. It helps you figure out, well, what exactly, because half the battle in terms of learning a programming language or learning a methodology is understanding why it was created a certain way. So it helps if you know why structures, you can use it as a reference variable and how it knows where all the data is. Same thing with an array. And then you can kind of see, well, you can pass an array to a function, but it's always treated by reference. But a structure you can do both ways. Then you can start seeing the inconsistencies in the language and go, I can return a structure from a function, but I can't return an array from a function. And I can't have a function that's an array type, but I can have a structure. I can have a function that's a structure type. But they're both implemented the same way. And then you see that, what do they call it, orthogonality, when it's like, doesn't match. It's inconsistent. And that's one of the main reasons why a lot of students have a hard time learning C++. It's a hard language to learn because it's just like the English language. It takes from a bunch of different sources. And there's no consistency in terms of the grammar rules. Some things are legal to say in certain contexts and some aren't. So you spend half the time learning all the rules. Which makes it a challenge, actually, compared to some other languages which follow a pattern, like based on Latin or something, or based on some sort of a predictable pattern that all the rules apply in the same way. Anyway, That was my little tangent on programming language concepts. Okay, back to C++. Here's an example of passing the structure by reference. And now we see this ampersand here, and we have that. This guy, as I mentioned before, and I purposely put it over here to tell you that the ampersand symbol says by reference. So if it got an animal type, we could have put a space in here. We could have put this guy over here, which is more common. So it's more common to see animal type space ampersand or animal type. Or usually you see it next to the particular variable we want the address of this animal or the address of something, if you read it that way. But in terms of the syntax, we're using this ampersand symbol to denote that we want the address of, and we're getting the starting address of that particular structure. So it adds 1 to the age, so we say thisAnimal.age++. We're actually changing it, we're using it as a reference, and we're saying thisAnimal.age at entry +1. So at the entry we're adding it to +1. So we're referencing the direct memory location for what, and this is more emphasis on the pointer concept than anything else. We're referencing the direct memory location, which means outside of this function the age is going to change. It's going to stay permanent because every time we go back and reference it, we're going to see that the memory has changed for which this variable was stored at. And here's again animal data. It's void. And actually, in C++, you can actually put the word void in there. Some languages will tell you, why are you putting void in there? Just leave it empty. Most people would just leave it empty. Well, you can put void in there to emphasize the point. It is void. It's not taking on any parameters. In fact, you can get real fancy and say void main and then put void inside of the parameter list. That's a lot of voids, but it depends on what you were taught in the beginning. Some languages in the beginning required you to put something in there, not leave it empty, which is how that came about. Alright, so this obtains all the information about the animal type from the keyboard. So we're getting it from the keyboard and we're putting it in, which means we're not passing anything to the function. We're just saying, get the data. So we have a prompt that's going to say something, and then we're going to say animal type, this animal, character, response, and then have the user enter all the data members until you're done. And then it says, while the response is correct, return something. So the code for the getting is not in here, but it's showing you how you can populate a particular structure by sending it to a function, which is kind of interesting because, as an example, arrays aren't populated automatically. They're not populated automatically in Java either. Usually there's a for loop. So we go for, integer I is equal to 0. 0 is less than 20, and we have an array that we've declared as 20, or actually we'd say 19 if that was the case. We figure out how many spaces we need to fill. We create a for loop to fill all the spaces, and then we initialize the values to something. We can also initialize and declare it, setting the values by default as well, but I'll show you that later on. But long story short, we can't do that with a structure because we don't have 0 through 20. We don't have index values. Instead, we have names. So what's common in terms of initializing a structure is to send it to a function. And then the function inside of the function, there's a loop in there that says, okay, what's the name? What's the age? What's the telephone number? And you populate all the data items manually that way. And that way, you don't have to repeat all that code. Every time you want to populate a structure, you just send it to the function that says, get the data. And then it asks the user to enter in all the stuff. So we have hierarchical structures, not inheritance, not to be confused with inheritance. The type of the structure, remember, can be another structure type, so we can use structures inside of structures and nest them. This is called a nested or hierarchical structure, and they're very useful when you have a lot of information and you have much detailed information for each one of the records. And here's an example. Let's talk about machine recording, records for machines as an example. So information about each machine, let's say you're in a machine shop and you're going to keep track of all these machines. So you have an ID number, you have a written description, and you might have subcomponents of all this stuff. It's kind of like writing an English paper and writing an outline. In the outline, header number 1, you have the machine. The machine might have maintenance records, history, descriptions about the machine, how many's in stock. Think of it as like an inventory item if you wanted to. The history, the failure rate, the number of downtimes. You may not necessarily want to put all this in one structure. If you created multiple variables for this, you'd probably have over 100. Now how are you going to remember machine number 1, name number 1, machine number 2, name number 2? And believe it or not, I see this all the time actually. People don't want to use structures for some reason because they learned Java first and C++ was second, and they don't know what a structure is. And instead you see data 1, data 2, data 3, data 4, and you get hundreds and thousands of variables all over the place, and they're not organized at all. So that's why the structure is actually kind of an important user-defined data type, because you can organize your data a lot better. So let's organize some data in terms of this machine shop. The concept of the date can be organized. So we have a structure date time, and the date time's got month, day, and year. And then we have a structure called statistic type, where we're going to keep types of statistics that are associated with it. And we could have like the failure rate, the last service date, maybe also maybe the downtime. And every time we have a date, and the date's actually kind of common because people like to store dates. So we can create an abstract, user-defined abstract data type called date, my date, or date type, and define the date any way we want, and then create variables of date. And so we have variable dates. So it's kind of like a database actually, think of that. Date, you can have any date types you want, month, day, year, month, date. Present it any way you want, store it any way you want, in any type of precision. Julian dates instead of real dates, which is what you're doing in the first programming assignment. But you're not using structures in that, so it doesn't really matter. And here we have the machine record. And the machine record has the statistic type in here for history, and statistic type is using date type. So this is what's meant by the hierarchy. You can put a nest of structure inside of a structure. And you see these are all separate declarations with semicolons at the end of each one. And they all come together, and they're all in sequential order. So if I put the date type on the bottom, the compiler is going to complain. So we don't know about date type. So when you put this in your .h file, put them in order of the hierarchy. And then plus people are used to reading them this way. Yes, I know about date type. Here's the date type. Yes, I know about statistic type. Here it is right here. And then you can kind of see how it works together. And then we're going to make one variable, and we're going to call it machine, and it's going to be a type machine record. It's going to include all of these other structures in there. And this is what it includes. If we looked at the memory that's associated with this, because we can still send this by reference if we wanted to, and get it and look at the memory. Here's our memory. We have our outer structure, and then we work inside, and we keep going in and in and in. So we can say machine.history.lastservice.year. They can't do this in C++. Well, can you do this in Java? You can nest a class inside of a class. I don't think you can. So, but you can do a structure inside of a structure inside of a structure. Superclass, yeah. But that's inheritance though. Well, not really. You're right, super. This and super is the equivalence to this, but you have to say super to go back to the previous, to the previous, to the previous in terms of the inheritance that's going on. Yeah. So this would be included, well, for those people who know Java, this is the super. But in C++ and in terms of the structure usage, you're just going in and you're using the dot notation here to resolve that we want the year that's inside of last service, that's inside of history, that's inside of machine. So we just resolve it in and using the dot notation. And the name of the particular variable that we're going into gives us our space allocation in terms of how it's stored in memory. So I like comparing one language to another because it kind of makes it more interesting. So it kind of goes back and says, yeah, because I know every language pretty much does the same thing. They just, well, I shouldn't say that. They don't all do the same thing, and they're not all equal, but some languages are implemented differently. And it's interesting to note what's different. This is something that doesn't exist in Java, the structure, which makes it interesting. So let's move on to unions. I already talked about unions, and I told you everything about unions already. It's a structure. People call unions, they call them lightweight structures. Can we keep it down in the back? So I don't have to, okay, thank you. So what is a union? It is a structure, but it's more memory efficient. take a look at all the memory that's located here, that's allocated every time you make an instance of this variable. Every time you create a new variable, it includes all the reserved space for all of the stuff needed for everything because it assumes you're going to use it all. And then you can start nesting structures inside of structures, and that's a lot of memory that's reserved for each one of those data types. Union says we're only going to use one at a time. Makes it easier. And if we're only going to use one at a time, then keep in mind this was prior to object orientation. We can have polymorphism. We can have the same variable in some instances of the program store an integer, and the same variable can now store a float or a double or anything we want it to do. So not only does it morph and change as we use it, and this was actually kind of the predecessor to, well, let's have polymorphism in terms of the concept. Let's put it in C++ object orientation and make it part of the class implementation. So the structure and the union both ended up being part of C++ in terms of the theory. So look, the formal definition of the union is a structure that holds only one of its members at any one moment in time in terms of the execution. You can't store more than one data member. It is declared in the same identical way as the structure, except for the keyword union is used instead. So we have union space, the name of the union. We still have the semicolon at the end of the declaration, but only one at a time of these can be used. So we say it's going to be a long, an integer, or float. So what do you think the compiler does? Reserves the space needed for the biggest one. So it picks out and says, well, what's the biggest requirement? And so then it can accommodate the biggest data member that you might actually assign. And then if we don't use the space, and here I'd say probably the long or the float is probably contending for the biggest space. Probably the float is going to be the biggest, but it's going to say can reserve a space equivalent to float, and maybe you'll put an integer inside of a float space, and that'll fit just fine. But you don't want to have it too small because you won't be able to put the big one in. So it accommodates the largest data. So you could still end up with a situation if you included inside of the union a structure, which you can do. Let's say we put animal type inside of that union. It's going to reserve all that space anyway. So unions are not normally used as a substitution for structures to save space. They're more used for lightweight polymorphic type of behavior, in which we're not planning on having the weight type stored in all of these different types, but we don't necessarily know what type we're going to get, and why do we want to convert it? You think of the concept of C++ as a strongly typed language. You can't take an integer and add it to a float, or vice versa. You get a type mismatch error complaint coming out of the compiler. So the reason why, or one of the reasons why unions are popular and still being used outside of the memory associated with it, is that we have polymorphic. Now we can take one type, weight type, and it can be used as a long, an integer, or a float. It's storing one value, but we have 3 different data types to choose from. So if we took weight type and added it to an integer, we're not going to get a type mismatch error if we're storing an integer value. And we can also take and do the same thing with float and long. So gives us our polymorphic, and then it changes our type depending upon how we're using it. So here's an example of using the union. So we have the union weight type. Can we keep the noise down? It seems to be awfully loud in here today. Oh, thank you. So usually if I just stop talking, everybody else stops talking as well. So they go, what happened? She stopped talking. And then I start talking, everybody starts talking again. And then we have a huge hallway. You can take it outside if you want. Got plenty of room out there. All right. So what do we got here? Union weight type, and now we have weight type weight, and now we have weight type dot weight in tons. This is how we assign the value, and that's going to be a float. If we took weight in tons and we assigned it an integer value, we're going to get an error message. Well, actually not. I would convert it. If we took weight in tons and a float and we assigned it to an integer, actually it would convert it, but we're only going to get an integer instead of a float being stored. So the weight in tons is no longer needed. The memory can be reused, actually. So In this point, we have allocated memory for weight. We've allocated space for all three, theoretically. When we assign it, when we declare it, it says, oh, we're going to use float. Then we can get rid of the rest of it. We don't have to waste that memory. So weight in tons is now, weight in pounds is equal to 35. Now we get rid of it, we change it, and now it's stored in integers instead of floats. So we morph it and we change it. But in reality, the biggest space is reserved because we don't have, and this brings up kind of an interesting concept and another difference between C++ and Java. Java, everything is dynamically allocated. All of the memory is allocated at runtime. Because if you remember Java, we got a JVM, Java Virtual Machine. We have an environment out there for which we have a stored class, and until that class is executed, until it actually gets brought into memory, we haven't reserved anything yet. C++ is the exact opposite. At compile time, everything is statically allocated. We have no well, I shouldn't say that. We have some dynamic capabilities, and we're going to look at them in this class. But for the most part, what we're looking at right now is static allocation, which says we have to prepare for memory when the executable program gets started, gets loaded into the runtime environment. We have these things called activation records that end up on a stack. And then we have memory that's allocated within the process space of this running program. And we're organizing this memory, and we're adding stuff to the memory. We've already pre-decided our entire configuration and how much memory we're going to need. And we're not going to compile unless we have enough memory available, unless we can be configured. So in some ways, we have already decided what we're going to do before we even started, and everything is preset. Which means if we're going to make a weight type, we're going to have to make it as big as possible, considering all the other choices we might have. So that's why I'm saying we have the biggest type there reserved already, and so we don't use, we don't actually have to reserve everything. We don't have to have 3 spaces. We only have 1 space, but it's the same size as the biggest one we need to store. So let's talk about abstraction, because we're actually going through the history of C at the same time, leading us into C++, which, if we think about the concept of abstraction, we've created data abstraction, which is why we have the abstract data types. We all know about data types. I started out talking about built-in data types, floats, doubles, integers. We've progressed into abstract ADTs, abstract data types. We've talked about creating the concept of the data storage in terms of the structure, the union. We can have the same concept in terms of arrays, but we're still using basic structures and constructs. I should not call them structures because now you're going to think I'm talking about structures. So abstraction, for the most part, is the separation of the qualities of the object from the details of how it works or how it's composed. So when we use a union, we use a structure, we use a class, we don't really care about what's implemented inside of it. We just use it as a structure. We say we have weight, we have date, and we're using it like any other variable type, data type that we've been using so far. So this is where that kind of the distinction falls through in terms of, by definition, it focuses on what and not necessarily how, which is how you can kind of build a repository, and I'm not using the word library on purpose. You can build a repository of all of this functionality, and you just use it. Oh, I need a date. Date. I need a time. Time. And you're building. You're not building a library because that would be more of a hierarchical class structure. The repository term is more like a collection, and so you build a collection of abstract data types and you use them inside of your programs. It has nothing really to do with object orientation, but it was the kind of the start of the thinking in terms of how are we going to extend the language, how are we going to customize it, how are we going to make it work for all these different types of projects that we might have in terms of functionality. So who is talking? Can we bring it outside or something? I think it's my TA who's talking. Can we talk it outside? Yeah. All right. Maybe it's not you. I know it's coming from that area of the room. Okay. So it's necessary for managing large, complex software projects. So what I've been showing you so far is referred to as data abstraction. we also have the flip side of that, control abstraction. Control abstraction separates the logical properties of the actions from its implementations. So the data is the data members, the control abstraction of the member functions. It's the functionality, it's the procedures, the processes. For example, the implementation of a search. Do we really need to know what the search does? Or we're going to say find this, find that. That's a control abstraction, because what is search? What is find? It's something where we don't have to think, well, it starts at the beginning of the list and it looks for the first character, the first name of the blah, 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 and it goes through this sequentially until it doesn't find a match, and then it comes back here. We don't care about all that stuff. We just want to search. We just want to find. So the function call depends on the function's specifications or its descriptions, not its implementation or its algorithm. So we say, search for this list item, in this list, this item, this length, where found. Now tell me where it is, tell me where. And these are formal parameters that we're sending as to this particular function call to search, which is where a method comes from actually in terms of functionality, and which is why we have that natural translation from a structure to a class, because it's really the same type of concept, we've just added more functionality to it. So on the flip side, we have our data abstraction that we've seen already in terms of what we've been doing. We're separating out the logical properties of the data from its implementation. The logical properties would be, what are the possible values that we can store? What operations will be needed for the storage? In terms of the implementation, it might be, how can this be done in C++? And how are the data types, what data types are we going to use in terms of the data abstraction? Well, we have a lot of things to pull from. We have a union, we have a structure, we have a class. We have all sorts of different constructs that we can take into consideration. So, data types, and what I'm leading to is the concept that the class is nothing more than a data type. and that's essentially different kind of thinking than Java. Java actually will only have one main object, and that's the class in terms of its implementation. In C++, it's like, it's a data type. It's nothing more than an abstract data type, and it can be used with other abstract data types because we have other ones. In C++, we have a selection. In Java, we don't. All we have is this object. So that's why I always say that Java is purely object-oriented programming. We don't have a choice. We have to use objects for everything. C++, we have both. We have a choice, which is interesting. So going back to the data type concept, if we think about classes in the background, we think about structures, we think about integers and floats and doubles and everything is a data type. Then we have the data type, which is defined by the set of values or the domain. So an integer goes from, well, if it's a signed integer, goes from negative something to positive something on the number scale in terms of whole integer values. We have an allowable range of operations that we can perform on them. We can add them together. We can, here's our values here. For integer is a data type. It has a negative, who knows, I don't even know if that's really true. I think it was expanded in recent history because memory gets bigger anyway. But who knows how it's, and actually this particular domain can be different for each programming compiler. Every language and every programming compiler. For example, Borland C++ might have a different definition than Microsoft C++ versus Bloodshed compilers or Dev C++. The range has to do with how much memory management and the utilities that are involved and how much space do we want. Depending upon how big we make the range, we might need more or less space for the allocation. The operations, it depends on the programming language, syntax and semantics, and the implementation. Do we want to be able to concatenate? Maybe we're going to use plus plus for concatenation instead of incrementing. The idea about being able to use the plus plus is actually kind of interesting, or the minus minus, or the equals equals. And what does the equals equals mean? Well, it's defined by the allowable operations. So equals equals is a comparison normally. So in terms of our C++ implementation of the abstract data type, it's a programmer-defined type. So it's a set of values, allowable operations, and some may define C++ types. This is where I say we have variety. We have the structure, we have the union, we have the type define, and we have the class. We don't have just the class, which makes the language a little bit harder to learn, but yes, yet more flexible. And here's our major flexibility that a lot of people wish would go away. And that's really, in some cases, bad practice and by some programmers, and is not a feature of Java. You cannot do this in 99.9% of any more programming languages these days. And once you figure out what this does, you'll probably figure out, well, now I know why. Type define. It's just like a structure, just like a class, just like a union. It's an abstract data type that we're creating, but it's doing nothing more than a rename, and it causes confusion, and it actually, as I was saying before the class started, it leads to a lack of readability in terms, adds to writability, removes readability completely. You're looking at somebody's code and you're going, well, what's a Boolean? Because here we have a Boolean. The data type doesn't exist in the C++ language, but now it does, because we've said, and think of this as a rename. So in DOS, if you said rename integer space Boolean. Now, every time I say Boolean, I'm really talking about integer. What if I don't like the way int is spelled, and I want to say type define space int space integer, intger. Now I can use integer as if it were an int, or Boolean as if it were an int. And then you look at that and read somebody's code and you go, Boolean? Because you know this is going to be in a header file. It's not even going to be in the source code. You're not going to see it at all. Instead, you're going to read somebody's code and you're going to go, my Boolean. Who knows if that's an integer, a float, a double? Who knows what in the world that is? And you got to go spend time looking it up to go see what in the world you're talking about. That's what I mean by it removes some readability from your ability to understand the source code that somebody else wrote. Obviously, this came and it started out with C, and it came from, let's learn C. And people say, well, why do we want to learn C? We know B, or we know Fortran, or we know COBOL, we know, and now we have different names for the data types. So it allowed C programmers to make the language interface look like what they're used to. Let's call them, let's make, okay, you can change the names of all the variable types and you can use what you want to use. So essentially, it's a crutch, and a lot of things actually have been added to C over the years that have ended up this way, like the enumeration. And even kind of some of the pre-implementations of the array concept ended up out of, oops. Oh, that's not good. I think my computer has a mind of its own today. It's suffering from heat stroke or something. I don't know. It was sitting in my car too long. Okay. It actually seriously was. I think I have had some heat damage. I might have to send this back to Apple. So. All right. Well, if you see me with a different computer next week, you know why. It sat in the car too long. All right. Actually, you know what? I recently discovered, I thought it was a Mythbuster. Have you guys seen Mythbusters? It's a show where they say, they used to say if you leave a computer in a car, it doesn't damage it. Like, it doesn't have any, like computer electronics and things like that, if you put them over 100 degrees in the trunk of a car or something like that, there's no damage. Don't have to worry about it. Just like you can take your thing and put it through the metal detectors and scanners and stuff. Well, they put a cell phone in the trunk of a car and it melted. The board pieces melted, and the plastic shielding melted onto it and made the connections not work correctly. So it's not a myth, it's true. You leave your computer in the car in a 90-degree weather, 100-degree weather, you're going to damage the computer. And there's evidence. He just saw it a few minutes ago. My computer's acting funny today. Mythbuster solved it. All right, back to the lecture. Not quite as funny, but type define. So here's our example. So we have type define integer Boolean, rename integer to Boolean. Character string. We've got character string 20. And this is a array that we've created here of 21 character strings. We're going to call it. Now we have a message, and we have a message here of 20. That's message, variable declarations. Now we have Boolean senior citizen. And you're looking at, if you just saw Boolean senior citizen and everything else was in all of these two were in a header file, you might go, well, what data type is Boolean? Wow, C++ has advanced. Now we have Boolean as a data type. Causes confusion. Here it is. Using a structure, type define, inside of a structure, type define character string 20, and declare the structure. We're going to call it employee type, and inside we have name, that is of string 20, is our new data type. So you can nest type. You can use type define anywhere, and you can type define anything you want. Actually, you can type define structures to other structure names. It's normally used in limited purposes for things in which you just need to call it something else, because you don't want to have the person know that this is actually an array string, an array of 21, instead of just, you know, what is name, you know. So, and what is this? We made an instance of this particular variable, and we called it myself. It's in a variable type of employee type, and then in memory we have 21 characters for the name. It's actually an array of 21 characters that's in here as a string. So myself. So we can see how the memory is allocated. Which, you know, if you think about the concept, structures do take up some memory because we're allocating for every one of the data types that we've put in there. So, going back to our abstract data type in terms of its definition, it's whose properties, domain, operations are specific. So we create them for particular implementations, and we use them independently of other structures. So once we create it, we have it, and we can use it. In terms of its definition, the type here, we have type. Let's say we're going to create a type, and we're going to call it time type as another example. It's going to keep a, you know, month, day, year, or time. No, I said hours, minutes, seconds. I'm sorry. So we have the domain that we specified. And this is a classic way of documenting, and it actually follows through with the implementation in a lot of ways, because we have a type, and then we have a domain of our allowable values, which is going to be hours, minutes, and seconds, and then we have operations that we might want to do on this particular time type. And this is where the concept of the class actually comes from, and why in C++ we somehow, a lot of people from tradition start out with data members first, because they're talking about the domain first, and then they follow through with the operations second. And then you have another breed of people that switch the order. They present the operations first and then the data second. So it depends on, it could come in any order you want, but it depends on your preference in terms of how you're viewing the abstract data type in terms of its definition. So some operations might be set the time, print the time, increment 1 second or something. You know. Then we might have another abstract data type, as an example, complex number type. Could be each value is the ordered pair of real numbers, A and B, let's say, because we don't want to keep just one number. We want to have this complex number represented by you know, some notation, and then we have some operations for add, subtract, multiply, divide, and then we can implement those in terms of the construct that's available to us in the language. So choose a specific data representation for the abstract data type that already exists, back to built-in or program or defined type. So all the types are actually written by previous types. So the structure itself is a type. It's a type structure. And you create structures of the particular type that include built-in data types or other types. So types in terms of this particular language implementation are all, any type is inside of a type. So you're just basically defining your own types. So writing functions for allowable operations exists. And that gives us the abstraction barrier and creates this concept of information hiding. So now we're going to kind of switch gears a little bit and start talking about classes in terms of its implementation. And one of the reasons why this sort of came out was to promote the concept of information hiding. And information hiding gives us, you know, a barrier in terms of complexity. So if we get rid of the implementation and just focus on what functionality, what operations, and we focus, essentially we change our focus into these categories. We have the type that we're considering, the domain, and the operations. And then we can kind of define it in terms of its implementation. So the class implementation details are hidden from the client's view, and this is called information hiding. So we have public functions of the class in terms of its interface between the class code and the class object. So we end up with a specification and an implementation that has a little barrier in terms of abstraction that goes on. And this is actually simplified in Java. And it's a little bit, it's separated. For some strange reason, it's separated in C++. If you think of the concept, Java was actually part of C, it was rewritten, a better version of C++. Not to say that C++ object orientation, there's anything wrong with it, but it took all the inconsistencies and made everything consistent and just gave us an object. It gave us one thing to work with. In C++, we actually have things called interfaces in terms of the details of the implementation, and then we have the specification of what it is we're going to use this class for. So we break out the abstractions into a couple of different layers, if it makes any sense. In terms of the complex, excuse me, the content of what is meant by information hiding, it's separating out, so we hide the information of the implementation and we use the specification. So this actually goes, well, I'll just repeat what I said earlier today. I actually was thinking about this earlier, or just a few minutes ago, thinking about what I said in the previous lecture that I gave today in terms of the .h and the .c++ files and how that kind of differs from Java. Because when we say include iostream.h, we have the specification for what we're going to call the cin function, the cout function, and those methods. And right now, cin and cout are the only two I've really presented to you in terms of iostream.h. But we don't see all of the details of everything. We don't see how cin and cout, and if you look at that, the code is actually quite long for how that is actually implemented. But we include the .h file. So C++, in terms of the information hiding characteristic, was designed so you include the specifications, which are in the .h files, and you can quickly look, if you were going to look in that .h file, you could find, oh look, there's cin, oh look, there's cout. These are the functions that I can use. And then when the compiler goes ahead and creates the executable code for you, it'll go and find the object code and put it in there for you. And it will supply the implementation for you. But the user isn't given the implementation. The user is only given the header or the specification. So third-party libraries. You got a scanner. Usually you think you're going to give away your code. No. No one's going to give away their valuable source code about their drivers or their scanner functionality. But in order to use this scanner, as an example, you're going to write a C++ program that's going to interface with this scanner. It's going to take a scanned image and do something with it. You gotta have the specification for what library calls there are. You know, is there a read? Is there a write? Is there? So they give you the .h file, and you include the .h file in your source code that you're writing. And then when you go to compile it, it goes out and looks for the object code. Well, the object code is a binary format. It's already it's intermediate code. It's not necessarily, excuse me, I shouldn't call it binary. It's intermediate code. It's assembly/machine language that's ready to go to turn into the final binary of your program. And so you can include the .h file. And when the compiler reads the .h file, it's only getting the specification. It's not getting the implementation. All that information is hidden from the particular programmer. It's for safety reasons, but it's also for efficiency. If the compiler had to read through every single one of the lines of code in those .h files, it would be like the old days when we didn't have it separated. In the old days, how long did it take you to compile a program, hello world? Maybe an hour. You'd start the build, you'd go to lunch, you'd come back, and maybe the build would be done. For anyone who remembers pre-everything, like right in the beginning when C compilers were first available, it took you hours. You didn't want to compile it because it took you hours to compile it. So you set the build, you went home, you came back the next day, and it was built for you. That's because we didn't separate everything out into object code. We didn't have specifications and implementations. We had it all in one. Nothing was hidden, everything was given to the programmer. You can go ahead and change the source for something right there because nothing is compiled. So we have this concept called precompiled headers. And then those are what you're actually including. So when you go ahead and you write your own classes in C++, you follow the same format. You create your precompiled headers. and you use your classes inside of other programs. So you can write your own implementation of C in, C out. You can implement it off of the specification of the .header file. When you use your classes, you include the .h files, and it goes out and finds the object code that you've already compiled for your hello world whatever object that you've created. And we'll see that when we start implementing classes, which we're not going to do this week. We're actually going to do it next week, because I think that it deserves its own lecture. In Java, you'll see you just create a .java file. Everything's an object. In C++, we have to create a .h file, and then we go and create a .c++ file, and then we can compile that, and so it sits there waiting. And then when we use the file, we include the .h file, and then we call these classes. We make instances of classes that are specified in that .h file. And then when we go to compile that program, it goes out and uses our already compiled .o files that we have already created, that are the implementation. And voila, we have a working program. So it's a little bit, we have more pieces because it's all separated out. It's separated out because it's supporting information hiding. Because once you create your classes, once you have your system, you can use those as libraries, give them to somebody else so that they can use it for your scanner, their scanner, somebody else's hardware device or something, and you're not giving your code away. So different in concept than Java, actually. Java is more user-friendly. Everything is a .java file. Everything gets created into a .class file. And you start and load .class files, and one .class file goes and gets another .class file, goes get another .class file. And the problem with Java is being able to locate all your class files, set your environment correctly, and configure security within the environment to share the files. Different kind of thinking, because you only get one file with C++. Now one file has all the object code that's already compiled for you from all of the other things that you've created. Because we don't want to sit there and wait all night for our program to compile. We want to see it done in 2 seconds. So why reinvent the wheel every time you're going to compile it? But it's a pre-compiled, static, compiled language. It's not a hybrid language like Java is. So long story short, if you haven't understood any of that, consider the differences. In C++, you have to wait for the program to compile. But once it compiles, it runs faster. Because it's all done. It's already pre-configured, already set. So when you double-click on that icon, that program is fast. Or you could have a really quick compilation process because there is nothing. You just create new class files and add it. But when you run the program, it's slower. So Java runs slower than C++, but it compiles faster. So because you got 2 different working environments. And back to finish up the benefits of information hiding. Data and data details are concealed from the client abstraction. C++ has the concealing. Actually, you can have true information hiding in a C++ environment. In Java, not so much hidden. Not so much hidden at all. Code can be changed without affecting the client because the specification and the interface are unchangeable. So you leave the interface the same, and you change the implementation, and you leave the specification, or you can add stuff to the specification if you want, and you can extend without having to you can recompile and replace object code without the program malfunctioning. We can make improvements and extend and still keep the same functionality going along as long as you keep the public interface the same. Which is kind of the concept that Java uses as well. Java supports the public-private protected interface, but their use of it is primarily for inheritance and for preserving the quality of the class and the implementation of the class. In C++, we see that, plus we see preserving the protection of hiding the details of somebody's specialized driver, somebody's library, somebody's third-party tool that they gave you to use that you can include, but they're not giving you the source code for it. They're going to give you the object code, and you include the object code. Java, you just decompile it. You see all the object code. You see all the source code. No problem. So not as secure. Which is why actually there are some C++ people that take Java code and turn it into executable files, encrypt it, and they add a whole bunch of protection to it. Because you can do that. You don't actually have to run Java files in an insecure Java JVM environment. You can compile them to an executable code, and it will actually run faster. So, but it takes a third party. It's not supported by Java, although it works, and it will take a little bit extra time, and it creates a bigger file essentially, but it runs faster. All right, let's look at the type time just to finish this up, so I should find a good stopping point for next time. So we have several possible representations of the time type. As an example, we can have 3 integer variables, hours, minutes, and seconds. We can have 3 strings. We can have an array that keeps it all into. So we can have separate implementations of the same particular concept when we create our type. The actual choice of the representation depends on the time, space, and the algorithm that's needed to implement the operation. Some possible representations here might be a structure with 2 float members in it, maybe 2-element float array or something. So the implementation can be separated. Oh, this is good stopping point actually. So the implementation, the point being made with this example is it's separated. We have different implementation choices. We can create the same objects. Same concept actually exists in Java. We can do the same thing. So we decide we want this thing called a complex number type, or we're going to call it a time type. Maybe an easier example to look at. How we implement it doesn't matter. When we create the object code, we know we can call this function or make an instance of this class that we're going to call time type, and we just use it. So that's actually what's referred to as the information hiding component. Next time I'll go through and we'll start in with the concept of classes, which really deserves its own lecture. And we'll see how classes, and I've kind of made it sound difficult, but I don't think it is as difficult as I'm making it sound. We have more than one file. We have 2 files that we created in, and if you want to do it properly, and to support information hiding. We can break the rules and put everything in a .c++ file. We can get away actually without using header files. But it's kind of like, you know, you're writing hello world and you don't include iostream.h. Instead, you include all of the source code for C in and C out and all the functions that you're going to use, because in order to use them, you have to define them right there in the file. And your hello world ends up being probably about 12 pages long, when really it could have been maybe it could have been 4 lines of code. So if you want to make your language writable, then you use header files and you include all the functionality in, and your program is very small and everything else is included. So we do that with classes so that we can include the header, include all of the specifications, and then we can build on those classes, we can extend those classes, we can use those classes without having to worry about all the implementation details that are associated with that. We still have it, we just don't have to worry about it. We don't have to look at it ever again. So, which is kind of like what we do in Java. In Java, you don't have to look at it either. You just have to locate it in the right directory. So, all right, so next time we will talk about classes, and then we'll get into more object-oriented terminology. So far, we've just hit data abstraction and information hiding. So we have encapsulation, polymorphism, concept of reuse, and stuff like that to talk about as well. So we get out a little 10 minutes early for today. No problem. Questions? Opportunity for questions right now? No? Now I finally quieted it down. All right, so I'll see you next week. Enjoy the heat or the